Dear students, in physics in the section electricity, now let us see another experiment. This is about finding the coefficient of resistance, temperature coefficient of resistance of a metal using the meter bridge, right. What is this temperature coefficient of resistance? You know, resistance of a material, right, electric resistance of a material increases when its temperature increases, right, which is given by R theta equals R naught into 1 plus alpha theta. This is the initial resistance. When it is at 0 degree, the resistance is R naught. This is the temperature. Alpha is what you call coefficient of temperature coefficient of resistance. So, basically when temperature increases by 1 degree, by how much resistance is going to increase is what we measure here as alpha. So, how we are going to measure this? We take the meter bridge. You all know the meter bridge. Let me draw the meter bridge. You will have the string on the meter bridge like this. Then this will be connected like this. On the other side, like this. On the other side also, in the middle. That's how it's going to be. Yes, that's the meter bridge. That's how the meter bridge is going to be. Correct? Now, what we do? We give the supply to this, right? Better if we give with a variable resistance also, and then the switch, right. Why variable resistance? So that we can adjust the voltage that falls into this meter bridge string. Suppose if you have this battery to be in 8 volt, if you don't want 8 volt, if you want only 4 voltage, then you can change this resistance and bring 4 voltage into this string. That's why we have a resistance. But if you think the battery and its voltage is sufficient for the string, you don't have to do any alteration. This might not be needed as well. This is the plug key or insert key. Here, let's connect a known resistance R. Here what we are going to do, we will connect that material. So, what we are going to do here, we are going to take a copper coil and we are going to find the temperature coefficient of the copper coil. So, take that copper coil and connect it here. And what will happen to this copper coil, right? If I go a little more in detail, we will have a beaker with water and this copper coil, look at this, will be immersed into water, it will be filled with water, and this is how we will connect it. That's how we will connect it. So that we can change the temperature of it. This will be heated. We will have a thermometer also to measure the temperature. There will be a thermometer also. Thermometer and a stirrer. We will have a stirrer also. Why stirrer? To ensure that the temperature of water that we measure is as same as the temperature of that coil. Right. See, you have to keep stirring it so that the molecules around the coil, they keep moving. So that the coil's temperature and the water's temperature are equal, to ensure that you have to keep stirring it. So, it's a beaker with water and stirrer, temperature to thermometer, you keep heating it. Here what we will have, the usual arrangement. What is the usual arrangement? You will take it a galvanometer, center 0 galvanometer and connect it. This will be a high resistance which will have a setup to short circuit as well. Yeah. You know why we use that high resistance? Galvanometer has to be protected from high currents. Suppose if the point that you connect here has a very high potential difference, then what will happen? Very high current will flow. To avoid that, you put a high resistance in series with galvanometer around 5 kilo ohms, so that the current doesn't go very high. After you find the approximate equilibrium point, then you can short circuit it, so that now you increase the current, because now you are almost at 0, right? So, when you are almost at 0, magnify the current and then find the exact point, right. So, now what we do, let us say at room temperature we do it at 30 degrees. At 30 degrees you measure this distance x, right, and then at 40 degrees it will be a different distance, 50 degrees it will be a different distance, measure the x, measure the x. All what we can say, if I call this as R naught and if this is R, x, so L, let us say L, right. On this side you have R, on this side you have R naught. Here also it must be in the same proportion. So, the distance here is L, relevant to R, R is here, R and L are parallel. R naught and all together is 100, 100 minus L. R over R naught is going to be L over 100 minus L. Clear? Clear? Right. For this R, what you can say, R is going to be, or let us not call it R naught, let us put it as the R naught I used there, let us put it as simple R, okay, simple R, simple R. And for this R, what we can bring that one, R naught into 1 plus alpha theta, R naught into 1 plus alpha theta. So, you write R naught into 1 plus alpha theta over simple R, L over 100 minus L, L over 100 minus L, correct? Rearrange it. R naught plus R naught alpha theta, L over 100 minus L into R, right? 100 minus L over L equals 100 minus L over L equals, take it to the other side, R minus R naught over R naught alpha theta. 100 minus L over L equals, check that whether we are right, or we can even keep, we will do like this, we will keep L over 100 minus L itself, and then when you rearrange it is going to be R naught over R alpha into theta plus R naught over R. That is how you are going to get the formula, right. So, let us take this in the y axis, L over 100 minus L we will take it in the y axis. Theta is what we are changing, take it in the x axis, theta is what we are changing, temperature. All others are constants. R naught is the initial resistance of that coil at 0 degrees, that does not change. Simple R is the other resistance we used in the bridge, R naught R. Alpha is the temperature coefficient, that does not change. Every degree increment, how much resistance is going to increase, that does not change. So, I can call this as M, can call this as C. So, you can see intercept is R naught over R, gradient is R naught over R into alpha. So, if you want to find alpha, you find the gradient and divide that by intercept. Divide that by intercept. Gradient over intercept will give you alpha. This is what the experiment is going to be. Have a look at the diagram again. Have a look at the diagram again. Right. So, we keep heating this. maybe every 10 degrees, you again find the equilibrium point, measure this length L. On the same side of coil you have, find the parallel length L. Then you can draw the graph L over 100 minus L on the y axis, theta on the x axis, you get a nice straight line graph. Clear? Let's see how we are going to do the experiment. Materials and apparatus: an insulated copper wire coil of about 100 watts resistance, 100 ohms resistance, 100 ohms resistance. A center zero galvanometer, a sliding contact, 2 plug keys, a lead accumulator of EMF 2 volt or 2 nickel cadmium cells of electromotive force 1.2 volt in series. So 1.2, 1.2, 2.2, so approximately 2 volt is what you are going to get. 0 to 100 degree thermometer, a water heater, a wire mesh. Once they even ask, why do you keep a wire mesh to heat it? You keep the wire mesh because you want to give the heat uniformly. If you don't keep that wire mesh, you can ensure the heat is being transferred uniformly. At some instance, the heat transfer might be high. At another instance, heat transfer might be less. By keeping the wire mesh, you give heat uniformly, and all the area of that bottom of the beaker will be heated uniformly. A tripod, a Bunsen burner, meter bridge, 5 kilowatts resistor, a resistor box, a rheostat, and connecting wires. That's all we need. See, this is the arrangement we are going to do. I already have explained it, right? So here on this side they have kept the coil, which we take as R theta, and the equilibrium on that side is L. So the balance has to be 100 minus L. This is the R, other R that we are using. Galvanometer, center zero galvanometer, 5 kilo ohm in series, and you have a method to short circuit that. Battery or voltage supply, the rheostat or resistor box. This could be resistor box, but then you don't need a resistor box here because you just need a constant resistance only. We are not planning to change this resistance, right? This R remains constant. So you don't need a resistor box for that. A constant resistance would be enough, somewhat equal to the resistance of this. So what you can do initially, you can measure the resistance of this with multimeter. Suppose if it comes around say 90, 100 ohms, you can put 100 ohm here, right? Because when the temperature increases, the increment in resistance is very minute. So if it is 90, that might go by 90.5, 90.8, that's how it's going to go up, right? So it doesn't make much difference. So almost equal to R, you can have the R here, it's constant value, but this has to be a variable resistance because initially we will have to adjust it. What we do, okay, to get the equilibrium somewhere in the middle, right, we put it equally. Why do we put it equally? To get the equilibrium somewhere in the middle. Why do we want it in the middle? So that the fractional error of measurement will be less. Imagine if you are measuring only 4 centimeter, 5 centimeter, then the fractional error will be the error divided by 4 centimeter, which can be big. Whereas if you can bring this equilibrium to middle, say you are measuring at 40 centimeter, error divided by 40 is a smaller fractional error than error divided by 4. So usually the measurements has to be increased such that fractional error can be minimized. So this is what I already have explained it to you, right? This is going to be the y-axis, this is going to be the x-axis. There is a plus here. Y-axis M X C. So gradient is this. You divide gradient by intercept, you will get alpha. Method: connect the circuit as shown in the figure. Close the switch K1 and leaving K2 open. K1 is the voltage supply to the meter bridge. K2 is the short circuit of that galvanometer's resistance. So that you have to keep it open until you find an approximate equilibrium point. Record the initial temperature theta. Stir the water well and obtain the rough balance point. Next, close switch K2 and obtain the accurate balance point. Measure and record the length L. Heat the water while stirring, and for every rise of 10 degrees in temperature, obtain relevant balance length L and record in the table along with the temperature theta. Obtain about 5 or 6 points of readings would be enough, and it's a straight line graph we expect. So you draw the straight line. It won't be through origin, there is an intercept. So you draw the straight line. From the straight line graph, you have got find the gradient, find the intercept, divide it, that should give you alpha. Come, let's see the experiment and see how comfortable it is. So, the apparatus required for this practical include mainly, this is the one we call it meter bridge. Meter bridge, we have used it in the previous experiment also. So, you know how to use it, meter bridge. And these are the connecting wires. Connecting wires to complete the circuit, we will be using these connecting wires. This is the high resistance that we use in series with the galvanometer, because you know galvanometer is high sensitive. So, if a high current flows through the galvanometer might be affected, it might get damaged. So, to protect the galvanometer, we use this high resistance. And this is a plug switch or plug key, or you can say insert key, right, that is a kind of a switch. This is the sliding contact. Sliding contact, we used it in the previous experiment also. What do? One end of it we connect it to the galvanometer, the other end we can touch it at different points of the string, and find out the equipotential points. That means the point where galvanometer shows zero current, we can find it. For that we are using this. And then this is the coil, copper coil, of which we are going to find the temperature coefficient of resistance. We have a beaker of water. Why do we need that? Because we have to heat this copper coil. So, we can't directly heat it. We will keep it inside this water and beaker with water inside that. We will submerge this coil and then we will heat it up. While heating, we may have to stir the water. For that, we are using a stirrer. This is a stirrer. And to measure the temperature, we have thermometer. We will be using a Bunsen burner. So, to keep this beaker on top of the Bunsen burner, we will be using this tripod. Yes. And then this is the power supply. We use this power supply to give the required voltage to this voltmeter. If you have a battery, Lagrange's battery, you can use that as well. Lagrange's cell or any other battery, you can use it. But you have to ensure until throughout the experiment, same amount of voltage is given into this system. You have to ensure that, right? Suppose if you use a normal dry cell, sometimes when you take longer time, because you are going to heat it from 30 degree to 70, 80 degrees, it might take a while. Within that time, if you are using the battery continuously, battery might reduce its, the voltage of battery might decrease, electromotive force might decrease. So, to avoid that, maybe you can use Lagrange's cell, or you can use a supply like this, which is connected to the main supply. From that we convert and we give a direct current supply. This is the rheostat. Why do we use rheostat here? By connecting the rheostat in series with this meter bridge, we can adjust how much of voltage falls into the meter bridge, we can adjust it. Otherwise, what will happen? All the voltage given by the voltage supply might fall into meter bridge. By connecting it in series with this rheostat, you know, when I change the resistance of rheostat, accordingly the voltage that drops into the meter bridge as well as rheostat will change. Because of that reason, we will be using this rheostat. Also, we will be using a resistor box. Resistor box will be required in completing the circuit. I will show you while doing the circuit, I will show you where it is going to be required, right. So, this is all the apparatus that is required for this experiment. Let me show you step by step how to make the connection, how to make the circuit to do this experiment. Right, students. So, let me show you the connection step by step. First, I am going to show you how you are going to connect the power supply and the rheostat together with this meter bridge. It's very simple. First thing, let me take the plus of this power supply. You can see the plus of this power supply, that is this red color knob. Let me connect it to one end of the meter bridge, to here, right. Right, let me connect it to one end of the meter bridge, right. Then the negative end of it, right, this one, the black color knob, the negative end of it, I am going to connect it to the other end of the meter bridge, See, this is the meter bridge, right? So one side I am giving the plus of the power supply, other side I am giving the minus end of the power supply. But I will not be giving it directly. As I mentioned earlier, I will be using a rheostat in the middle so that I can divide the potential in between the rheostat and the meter bridge. So first let me connect it to the rheostat. And from the rheostat, let me take it to the other end of the meter bridge. Right. You can see with that, the supply to the meter bridge is done. Right. Plus is given here, minus is given here. I have not used the switch here because the power supply has a switch in it. So whenever I want, I can switch it on, switch it off, I can use that switch. So you don't have to use a separate switch at this point. Understand? Right. Now let me show you, I told you using this rheostat, I can change the amount of voltage that falls into this meter bridge. I mentioned that. Let me show you using a multimeter. Let's change this resistance and use the multimeter to measure how much of voltage falls here. I'll show it to you. You can see that. Let me switch it on. Now you can see, look at the readings of the multimeter. It shows 0.775 or approximately 0.77. So we have 0.77 voltage, approximately 0.77 voltage into the meter bridge. Let me reduce this rheostat and see what happens. What I expect when I reduce it, proportion of this resistance reduces now. So there must be less voltage falling in here, more voltage falling into the meter bridge. Let's check that. Now, after reducing the resistance of rheostat, can you check it now? See, it has come to 1.1 voltage. We get more voltage into the meter bridge. If I increase it further, let's increase it. I increase the resistance of the rheostat. See what happens now. You can see it has come down to 0.5. So this is the whole purpose of using rheostat here. I can adjust the resistance of this rheostat and I can decide how much of voltage I need within the meter bridge. Right? Okay. So that circuit is done. Then let me show you what we are going to connect in between these two. Very simple. In one gap here, I am going to connect, in this gap, I am going to connect a known resistance. A known resistance. For that only, I am going to use the resistor box. Let me show you a known resistance. Right. Let me connect this resistor box here. I can remove, let me say I am taking 1 ohm out of it. See 1 ohm, let me take this 1 ohm out. Right. So with 1 ohm resistance, I am connecting this resistor box here. Right. Now the resistor box is connected in this gap of the meter bridge. In the other gap, what I am going to do, that is where I am going to use that copper coil. The coil, metal coil that has been given to me, for which I have to find the thermal temperature coefficient of resistance. I am going to connect it here. Look at it carefully. Let me just connect it now. Let's say I connect it like this. Let's say I connect it like this. Right. If I connect like this, see, if I have 1 voltage across this string, Same 1 voltage is going to be there across these two resistors also. So imagine if in case if both resistors are equal, suppose it's 1 ohm, 1 ohm, then what will happen? The 1 voltage will equally fall into each of them. So at this point, that means in between the two resistors, it is going to be half of the voltage, 0.5 voltage will be there. At the same time, on this string also, from 1 voltage to 0 voltage, the voltage uniformly drops, uniformly, because the cross section is uniform, even cross section it has. So the voltage drop, voltage gradient will be same, which means at some point on this string also there has to be a 0.5 voltage point. Then what I am going to do, this point and the 0.5 voltage point on this string, I am going to connect them using a galvanometer. So how I find that 0.5 voltage point, equipotential point, is using a galvanometer. Let me show that as well. We will take the galvanometer. Let me connect the galvanometer now. Look at this. Say I take 1 point from here. I take 1 point from here and I will connect it to whichever the end of, like either the plus end or minus end, because the galvanometer is center zero galvanometer. It can measure the current on both sides. So whether you give it a plus side or minus side doesn't matter. So I connected this point to one side of the galvanometer. From the other knob of the galvanometer, let me connect the sliding contact. Sliding contact. That's the sliding contact. Let me connect it to other end of the galvanometer. Right. So you can see galvanometer is connected here and the other end is to the sliding contact. So what I can do after switching on and after giving the power supply, I can touch it at different points and find out at which point it shows 0 reading. Right, at which point it shows 0 reading. So let's say at this point, let's assume I have not given the supply yet. Let's assume when I keep it here, it shows 0 supply, 0 current there, which means from this point to this point, whatever the voltage drop on this line, on the string, as well as the voltage drop here on the other line, because these two are parallel lines, must be same, because these two are anyway same potential. These two must be same potential because there is no current flow. So the voltage drop here and the voltage drop here must be same. Voltage drop here means you have only this resistance. So I into R is whatever the current that goes through that circuit, I into R is going to be the voltage drop there. At the same time, the voltage drop here would be, you know, the gradient, the voltage gradient, potential gradient, let it be K. So K into, if this length is L, KL is going to be the voltage drop here. So KL will be equal to IR. That's how we find out how much of voltage drops here. Then what do? We are going to slowly heat this up. The coil will be heated up. When the coil is heated up, what happens? When the coil is heated up, the resistance of that metal will increase. So R is going to increase. Whereas this R remains the same, resistor box remains the same, the resistance of this coil increases, which means proportionation of the proportion of this resistance increases. So more voltage drops into that resistance. After the temperature increases, more voltage drops into that resistance. Then to balance that with the string of the meter bridge, I need more length of the string because more voltage is required. More voltage is required. K into L, that is what the voltage, then L increases only, voltage can increase. So I'll get a bigger length when the temperature increases. Let's say first time I R1, here it will be KL1. Next time when the R increases with temperature, L is going to increase. So what we are going to do in this experiment, we will be heating this coil slowly. At different temperatures, we will find out the length at which the potential become equal. with, we are going to go for a graphical method. So at least 4 or 5 points we have to consider. With those 5 points, what points we are going to take? The temperature and the length it takes here to balance it. Temperature will take a 10 degrees difference, 30 degree, 40 degree, 50, 60, 70. We will consider those 5 temperatures, and each of those temperatures, let's find out the length at which equipotential is found here, and then we can do the calculations. We can draw the graph. From the graph, we can get the gradient, we can get the intercept. Using the gradient and intercept, we can find out temperature coefficient of this copper coil. So how are we going to heat it up? That's why we have this beaker with water, because we can't directly heat this copper coil, then the temperature will not be uniform. You can't measure the temperature. So better we will keep it inside the water and heat it up. This is how we are going to heat it. We'll put it like this. Right, we'll submerge it there and we are going to heat it. Right. So we'll be using a tripod. We are going to keep it on the tripod. Let me connect another 2 string wires here. We will be keeping it on the tripod. Under the tripod, we will be keeping the Bunsen burner. We will be using a wire mesh also, so that the heat doesn't directly fall on the glass beakers, right? So that evenly the heat is transferred to the beaker. So that's how we are going to heat it up. One more thing, you remember, whenever we use galvanometer, we don't directly connect it. To protect it from high current, we always connect a high resistance in series with that. So let me show you how we are going to connect a high resistance there. We'll take the resistance, connect it here. Right, it goes through the resistance. Then what should we do? We have to keep another switch here in parallel to this. We have to keep another switch here in parallel to this, because after we find the approximate point, we have to short circuit it. Because when we use it at the both ends, there might be high current. At that time only the resistance will be useful. After we find the point approximately, then we can short circuit it. So how do we short circuit it? Look at this. From this end, you connect one side to the switch. Right. Let me remove the plug key, and the other end has to be connected. So basically you are having a switch, a plug key in parallel to the high resistance that you are using. After you find the approximate balancing point, then you can put this key in, plug the key in, and you can make sure the resistance is short circuited. This is all the setup we have here. Now what we are going to do, we will fix a thermometer. And we will keep the Bunsen burner, and we are going to start heating this. So let me show you how we are going to heat it up with the Bunsen burner. So students, you can see we have kept it under the Bunsen burner, and it's being heated. I'll be mixing it, I'll be stirring it until 30 degree comes. Now you can see the temperature is at 29. So let's wait until it comes to 30. What we must do, when it comes close to 30, you take the burner out, stir it, put it in, stir it, take it out. Likewise, slowly we must take it to 30. Right. Otherwise, if you wait until it comes to 30, then by the time you take the burner out, it might go beyond 30. Right. It might go beyond 30. right. So, what we will do here, still it is at 29, still it is at 29, let us keep stirring it. You can see it is coming close to 30. Do not wait until it comes to 30. When it is close to 30, take it out. Stir it. Right. Now you can see it has come to 30. It has come to 30. So, at 30, what we will do? We will switch on this and check. Here you can see, look at the galvanometer, it gives you a plus reading. Now look at it, it gives you a minus reading. Still minus. Plus. See, approximately here, see, approximately 0 is here, approximately 0 is here. Let us close this switch now, so that the resistance, the safety resistance is short circuited. Now we will check, it is on the plus side, minus side, still minus, plus, right. At this point we get 0. At this point we get 0. Look at the reading for that, we get 26.5 centimeters we are getting for that, 26.5 centimeters we are getting. Let us switch it off, let it get heated further. Now what did we do? Now what did we do? We measured at 30 degrees. At 30 degrees, the reading we got is 26.5 centimeters. Let us write it down on the table first. 30 degrees, 26.5 centimeter. As I mentioned earlier, what we are going to do here is a graphical method of calculation. So, we need at least 4 or 5 points to draw a straight line graph. The plan is to take the length at 30 degree, 40 degree, 50, 60, 70. At those 5 temperatures, we will measure the balancing length on the meter bridge, and we are going to bring it into a graph format, right. And I will remove this key as well, because this key is closed only when you find the approximate point. Did you notice another thing? Right after I get the reading, I have to switch off the power supply, because if the power supply gives the power continuously, then the string on the meter bridge might get heated. Because of heating, the string might get elongated, then it might not be a straight line here. Getting the measurements might have error. To avoid all that, you just switch it on only when you want to get the reading. Right after you get the reading, make sure you switch it off. Now what are we going to do? We are going to wait until it goes to 40 degree. At 40 degree, we are going to measure the balancing length again. What are we expecting at 40 degree? Look at this. At 40 degree, compared to 30 degree, the resistance of this coil will increase. So, when the resistance of coil increases, look at these two, right. The resistor box's resistance will remain the same. We are not changing that. That remains at 1 ohm itself. Resistor box remains the same. Whereas, compared to that, this one, the copper coil's resistance is going to increase. So, what that means, proportion of this copper coil's resistance is increasing, because resistor box and the copper coil are connected in series. So, in series, if two resistors are connected, how much voltage drop into each of them depends on the proportion of those resistances. Now, when the proportion of this resistance increases, more voltage, slightly higher voltage is going to drop in this copper coil resistance, which means compared to 30 degree, at 40 degree, I can expect the balancing length to be a little longer than the previous case. It has to be a little longer. That's what we are expecting. So we got 26.5 centimeter in the first case. Second case, it has to be little bigger. It won't be much bigger. You can expect like 0.2, 0.3 or maximum 0.6, 0.7 centimeters bigger. Not much. Right. So let's see. Let's keep heating it. Now you can see the temperature is it's passing 34 degree. It's above, just above 34. It's almost 35 degrees, almost 35. Let's keep stirring it until it comes to 40. Let's keep stirring it until it comes to 40. Students, you can see it has come to 39, almost 39, right? I told you don't wait until it goes to 40. When it is coming close to 40, take the burner out and stir it. Let's see. Now let me take the burner out and see, still at 39. Maybe I can give it again a little more heat. It's passing 39.5. Let's take it out. Now it's at 40 degree. Now it is at 40 degree. Right. At 40 degree, again let's switch on the power supply. Check the galvanometer, positive. On this side, negative. Positive. Negative. Close to 0. See, approximately here we are getting 0. Approximately. Somewhere around here we are getting 0. Now what we do? We close the plug switch. Now we will check again. Right, that is where we get 0. That is where we get 0. Let's get the reading here. We are getting a reading of 27 centimeters for that. 27 centimeters is the reading we are getting. Let's note it down. 27 centimeters. At 40 degree, it's 27 centimeters. Let's switch off the power supply and let it get heated further. Now, what is the next reading we are going to take? We are going to take the reading at 50 degrees. At 50 degrees, right? We can remove this plug key as well. After we find the approximate reading next time, we can again find the, we can again close that plug key and find the exact point where the reading becomes 0. Students, you can see it's coming close to 49, 48 it has crossed, right? It's coming close to 49. Let me take the burner out and see whether it comes to 50. Not yet. Maybe I can keep it again. Take it out and see whether it comes close to 50. Yes, you can see now it is at 50. Now it is at 50. Let's keep the burner out. Switch it on. Check the approximate point. Approximately at this point we are getting 0, approximately. Yes. Let's close it now. That's the point where we are getting 0. The reading at that point is 27.4 centimeters we are getting. 27.4 centimeters. Let's write it down at 50 degree. Yeah. Let it be heated further. I can switch it off. Right. Let it get heated further until the next 10 degrees. Now we have got 27.4. Let's write it. 27.4. 27.4 is what we have got. What is the next reading we are going to get? At 60 degrees, we are going to see what is going to be the balancing length. Until then, we can remove this plug switch. We'll wait until it comes to 60. Maybe we can stir that until it comes to 60. Particularly when it is close to 60, make sure you take the Bunsen burner out. Heat it little by little, check whether it comes to 60. Students, you can see it has come close to 59 now. 59. Let me take the burner out and stir it. It's still 59. Keep stirring it. Maybe we can give it some more time. It's increasing. It has come to 59 and a half. Take it out and stir it. Maybe a little bit more. There you go. It has come to 60 now. A little bit more. Now it is at 60. Very close to 60. Let's switch on the power supply and see where it comes to equilibrium. On this side it's plus, minus, plus, minus. Approximately around this point you see close to 0. That's the approximate 0 point. Let's close this circuit now. Now let's check. Minus, plus, yes, around that point we are getting 0. The reading for that is 27.8 centimeters we get. From this side we get 27.8 centimeters. Let's let it heat. We need to get one more reading. Let's let it heat until it goes to 70 degrees and let's write down what we have got. 27.8 centimeters at 60 degrees centigrade. 27.8 centimeters. Let's keep stirring it. Make sure you have switched off right after getting the reading. Also you remove the plug key because that is short circuited only after you find the approximate 0 current point. Let's keep stirring it. Students, you can see it's coming close to 70. Let's take it out, stir it. Let's keep it in. Check whether it comes to 70. Now it is at 70. Let me take the burner out. 70, right? Let's give the power supply. Let's check. It's on the plus side now. Minus, plus, approximately around this point you are getting it 0 approximately. Now let me close this. Yes, at this point it is 0. That is at 28.3 centimeters we are getting. 28.3 centimeters we are getting. That is for 70 degrees centigrade, 28.3. Now we have got 5 readings, 5 different temperatures at 10 degree gap each of them, and the length at which the voltages were balanced, we have got it. What we can do now, as I mentioned earlier, we can draw the graph. On the graph, we can find the gradient, intercept. Using those two, we can find the temperature coefficient of this copper coil. Students, you can see the readings. I have put it in the table here. I need to calculate L over 100 minus L, right, which is going to be, see, 26.5 over, let's take it like this, 26.5 over, you will have 100 minus 26.5 is 73.5. So that's going to be, let's say, 0.4, not enough, 3, 5, 10, 22. This will be 6, 0.36. Next one is going to be 27 divided by 73. 3, 51, 5, 7, 7, approximately 7, 7. Next is 27.4 divided by 72.6. Let's see if 4 is enough. No. 3. Subtract it, you get 2, 6, 6, 1, 5. 5, 6, 20, approximately 8.38. You are rounded to 2 decimals, right? So it comes like 0.376 something, which is rounded to 0.38. Next one, 278 divided by 27.8 divided by 72.2. So still 0.3. 6140, 8. The thing is now this is going to be 37 something, this is going to be 385, let's say. Let me put 8 and see. 4, 6, 3, yes, 364. So it's around 38.5, 0.385, which I can write as 0.39. So let's write it as 0.39 because next one is going to be 5. See, 5 is enough, which means 39. If I am writing into 2 decimals, it will be 39. The next one is 283 divided by 71.7. 3, 21, 5, 21. Then you have, I think this time, no, 4 is not enough, 9, 12, 5, 7, 7, 1, 6. I mean 9, 63, 15, 63 and 1, 64. 7, 2, 3. So it's around 394. So this is also 39, but that was 385. 385. This is going to be 394. Shall we write it in 3 decimals? 3 decimals. This is going to be 0.38394. 0.385. What about this? 8 is not enough here. 3 decimals. 37. 42, 4, 8, 50. 8, 3, 5. 5, 3, 80. You will have 7. 377. What about this? You have 5, 10 balance there. You have 73. Then 6 will be 6 here. 18, 42, 43. Then you have 72. That's 9. 369. 3699. I think you can take it as 370. 370. Next one. 6 you have put. Let's see. 30. 21, 2. 42, 44. 400. 400 wouldn't have any. 360 or 361 it will be. Right? So, in 3 decimal we have all these values. Now, let us draw the graph. Theta is going to be in the x axis. L over 100 minus L is going to be in the y axis. Theta, you need up to 70 degrees. 70. So, 10, 20, 30, 40, 50, 60, 70. This is in degree centigrade. L over 100 minus L will not have units because centimeter over centimeter will cancel each other. L over 100 minus L, it goes up to 0.394. 0.394. So, how do we do it? 2, 4, 6, 8, 10, 12, 14, 16, 18 scales we have, 18. We need up to 0.394. We will take, if I take this as 18, so see like 0.394, 18, 36, 34 is 2. So, we will take 0.025 by 25, 0.025 by 25. So, let us mark this point as 0.05. Mark this as 0.10, 0.15, 0.20, 0.25, 0.30, 0.35, 0.40. That's good enough. First one 361, 30 degree 361. 30 degree 361, 35, 375, 361. Look at this 35, 361 should be somewhere here. Next 40, 370. 40, oh, I missed the point, it has to be a 30, 30, 361, it must be here. 30 is here. Right. 40, how much is it? 370. 40, 370. 350, 375. So, it has to be a little below that. 370. 50, 377. 377. 50, 377. Here. 60, 385. 385. 60, 385. 350, 375, 385. 70, 394. 70, 394. 70, 394. Right. Those are the points. Let's draw the graph. Seems that is the best graph I can draw. Just one point deviated a little bit. That's also like minute difference. All others fall on the straight line. As we expected, we can see y equals mx plus c. Now, the gradient, to find gradient and intercept, we need 2 points. See, this point looks good, which is at 45 and 37.5, 0.375. And let's take another point. See, this is good. This is at 20.35. So, we can get the gradient as well as the intercept. Intercept value 3.325. This is like 1/3 of that, another 25. So, it's approximately 0.335. 335. Now, let's say gradient is R naught alpha over R equals 375 minus 0.35, 45 minus 20. So, you get 0.025 over 25. Nice points we get. 0.001. 0.001. Intercept is 0.335. 0.335. Correct? 0.335. What is intercept? This is actually R naught over R. Remember the formula? What was the formula? L over L, 100 minus L, R naught R alpha into theta, R naught over R. R naught is the resistance of copper coil at 0 degrees. R is the other resistance we used in the meter bridge, other known resistance. Alpha is the heat resistivity or heat coefficient. Now, alpha has to be gradient divided by intercept. Gradient is 0.001, intercept is 0.335. So, it is 1 into 10 to the power minus 3 divided by 0.335. So, it is 1000 divided by 335. 335 if I divide by 5, it's going to be 67. 200 divided by 67. 67. You get 3 wouldn't be enough. 2, 134, 66, 0.9, 6, 60, 57, 570. You will have again 570. 295, no, not 295, 298, 299. So, it is 2.99 into 10 to the power minus 3. 2.99 into 10 to the power minus 3. That's how the resistance is going to increase for every centigrade. So, per degree centigrade. 2.99 into 10 to the power minus 3. You remember the formula? R theta equals R naught into 1 plus alpha theta, right? So, alpha theta should not have any units, because the other side you are adding that with 1. That means this per degree centigrade or this per Kelvin. Clear? That is what the experiment, readings and calculations are all about. Not so complicated, quite simple, right? Let us see the past paper questions that have come in this experiment. Alright students, now let us see some past paper questions from this experiment. The first one I have taken is from 1992. The following diagram shows some of the apparatus that can be used in an experiment to analyze the variation in the resistance x theta of a coil with its temperature theta. In this experiment, the temperature of the coil is increased to different levels and its resistance was measured using an electric circuit. Value of x in room temperature is 100. The given ammeter has a full scale deflection of 50 milliampere. V is a voltmeter, R is a rheostat. battery is 10 volt and the coil can be immersed within the water bath. Right, so that's the usual details of the experiment that we do, nothing new there. They have not completed the circuit, they have just given you the apparatus. Connect the objects in the above diagram and make a circuit that can measure the resistance of the coil at different temperatures. Right. So let's connect it. Let me take the battery and connect it to this end. Right. Voltmeter has to be connected parallelly, so don't take it in now. From the minus we will take ammeter. From ammeter we will take to the rheostat. We can connect it here. Right. From the rheostat we will take it here. Check that. So now what the circuit I have done is this: battery, ammeter, rheostat and the coil. This is what I have connected and this is what we are going to heat. So when you are connecting in the rheostat, be careful, if you have connected to these two ends, then you are using the full coil. It won't be variable. So you have to make sure you take this end, then the current goes through this way and it goes up. From this side you have to take it. Now this is the part of coil in the rheostat that you are using. Right. Another person could have connected like this also. Connect this here, this end and this end. Then the other side will be the part of rheostat that you are using. I have explained earlier also when we use the rheostat, how to use the rheostat. So remember all that. Students commonly make mistakes in this. Circuit is done. Voltmeter has to be connected. Voltmeter must be parallel to this. Right. So we know the current that goes through this coil. We know the voltage that falls across this coil. V equals IR. So R will be V over I. At different temperatures, we are going to find R. That's what they are trying to do here. They are not using the meter bridge. They are using the ammeter and voltmeter to find the resistance. What measurements will you take to find x theta? Ammeter reading. I. Voltmeter reading. V. What additional objects will you need to do this experiment? Let's go back to the diagram and check. Circuit is complete, but you need to measure the temperature. So we need a thermometer. Not only that, we need to use a stirrer to keep stirring it. Otherwise, the water's temperature and the coil's temperature, you can't ensure that they are same. When you keep stirring it, the water particles around the coil, they keep moving. They don't stabilize at a place. So when they keep moving, then we can ensure the water particles and the coil will come to a same temperature always. Otherwise, the water particles around the coil might be at one temperature. Water particles away from the coil can be at a different temperature. So what you measure may not be the temperature of the coil. Right. So what we need here, thermometer and the stirrer. What additional objects? Thermometer and the stirrer. Thermometer and the stirrer. Very simple, straightforward questions they ask. In this experiment, coil can be heated using 10 volt battery instead of using a burner. This method is not feasible, give reasons. 2 reasons they ask. See, instead of using the burner, heating it up, why not we send the current from the 10 volt battery through this resistance through this coil? Then you know P equals I squared R, then the coil will get heated. That way, if we do the heating, what is wrong is they are asking. Problem number 1, a 10 volt battery, to heat this coil and the water, it will take a lot of time. It will take a lot of time. Right? So the time that is going to be required to do this experiment will increase. Right? Problem number 1, 10 volt battery, or let's say it will take it will take longer to heat the coil. Another issue could be the battery may run down. Another issue could be, see, when we transfer the heat from water to the coil, it's quite easy for us to ensure water's temperature and the coil's temperature are equal. When you do it other way around, sometimes the coil might be at a different temperature. Why? Coil's temperature is keep on increasing. Water's temperature, from coil only the water has to get the temperature, the heat. So the water absorbs heat from the coil, and to show the temperature as the same of the coil, there might be a gap actually. Coil's temperature and water's temperature may not be always the same, right? Coil's temperature and water temperature may not be the same. See, these are some common practical issues. You don't have to have much, rocket science knowledge to answer these kind of questions. Very straightforward, practical questions they ask. If the voltmeter has a definite resistance, how would that affect the measurements? Now look at this. This is a circuit you had. Ammeter, variable resistance. This is the part that you are heating. So your plan is you are sending I, current goes through this, you measure the voltage. Right. V equals IR. So when you say V equals IR, R will be V over I. Now problem is, if usually the voltmeter is assumed to have very high resistance or infinity resistance, then the resistance between these 2 points means only this resistance, nothing else. But if voltmeter has a finite resistance, if it is not infinity, if it is not very high, it has a reasonably high resistance, then what will happen? The resistance between these 2 points is going to be the resultant of voltmeter's resistance and this resistance. Let me say this is R1, this is R2. Then the answer for R you will get by this experiment is going to be R1 R2 over R1 plus R2. You know how you get the parallel resistor, the equivalent. R1 and R2 are parallel, then the equivalent will be R1 not because 1 over R1 plus 1 over R2 equals 1 over R. Using that, this is what you will get. This is what you will get. So the experimental result that you get is not going to directly give you this resistance, that will give you the resistance which is equivalent to the voltmeter's resistance and the particular coil's resistance connected in parallel. That's what they are asking. If voltmeter has a definite resistance, how would that affect the measurements, right? So when this comes parallel, see if I connect R1 and R2 parallelly, the resultant R will be less than both of them. Do you know that? If you connect 10 ohm parallelly, resultant is 5 ohm. If you connect 10 ohm 20 ohm parallelly, resultant is 10 into 20 by 10 plus 20, 200 over 30, which is 6.67. If you connect 10 and 40 parallelly, that's 8 ohms. 10 and 40, 8 ohms resultant. 8 is smaller than 10, smaller than 40. So if you connect two resistors parallelly, the equivalent resistor, resultant resistance will be smaller than each of them. Smaller than each of them. So here the answer you will get for R will be smaller. How would that affect the measurements? The resistor or resistance measured will be, or resistance calculated. No, we don't measure the resistance, we calculate the resistance. Resistance calculated will be smaller than smaller than the actual resistance of the coil. What is the x theta versus theta graph that you expect in this experiment? We all know that x theta equals x naught into 1 plus alpha theta. X naught alpha theta, I'll write that first, x naught. Y m x, see, x naught means initial resistance, x naught, which is a constant. Alpha is the heat resistivity of the resistance, which is also constant. So x naught alpha will be the gradient, a positive gradient. The intercept is also positive. So the graph you expect will be like this. Theta, x theta, the graph you expect will be something like this, right? Upward sloping graph. Doesn't start from the origin, understand, it starts from the intercept. 50 milliampere full scale deflection ammeter shows its limit for the current in the circuit. How will you find the full scale deflection of the voltmeter to be connected based on this statement? Right. They say 50 milliampere full scale deflection ammeter shows its limit for the current in the circuit. So when the current goes, it shows the maximum, it shows the full scale. We'll go back and see here in the circuit. Right, look at this. When the current goes through here, right, ammeter shows the full one. That means 50 milliampere is going to be the current. It says it shows the limit, that means shows the maximum current, 50 milliampere. So when 50 milliampere goes through the circuit, the voltmeter, they are asking how will you find out the full scale deflection. So what you will do, now look at this. If you want to get the maximum voltage drop here, because they are talking about full scale deflection, right, of voltmeter. So how can you get the maximum current, maximum voltage across this coil? Think where and where the voltage is going to fall. The voltage of 10 volt will be partially here and partially here. Those are the only two resistors we have. Ammeter is ideal. We usually assume it to be ideal. So ignore the ammeter's resistance. If at all, it will have a small resistance, so we can neglect it. So 10 volt is going to fall in between these two. Even if you consider this, okay, all these three. According to the resistance proportion. Suppose this is negligible, then let's say this is 100 ohm, this is 100 ohm, equal 10 volt will go as 5 volt, 5 volt. Say this is 100 ohms, this is 300 ohms, 1:3. 10 volt will go divided as 2.5 volt and 7.5 volt. So understand, if the resistance proportion increases, the voltage that falls into the resistance also increases. How can I increase the proportion of this? Make this 0. That means push this to this, bring this slide to this point, so that you are not using any coil at all. It directly gets connected. Adjust the rheostat for 0 resistance and then see how much of voltage it shows. And that is going to be the full scale deflection. Right? It won't go beyond that. If at all when the temperature goes up, there might be a slight increase. Ignoring that, this is how we can find the full scale deflection of voltmeter. So let's say adjust the rheostat to 0 resistance and obtain the voltmeter reading. This will be the full scale deflection. This will be the full scale deflection. Clear? Next. That's all in that paper. So very straightforward, very easy questions. There is nothing much to be thinking too much, twisted, nothing like that. Now let's see another paper, 2010. You are asked to investigate the variation of the resistance of a coil of a metal wire with temperature and to determine the temperature coefficient of resistance. Same thing. The coil is formed by winding the wire on a wooden rod in such a way that no two turns touch each other. A Wheatstone bridge is to be used to measure the resistance of the coil. Wheatstone bridge, the usual meter bridge. Resistance of the wire at a given temperature is given by the equation R theta equals R naught plus 1 into 1 plus alpha theta. All the symbols have their usual meaning. Identify all the symbols. So R theta, let me write this big again. R theta equals R naught 1 plus alpha theta. R theta, resistance of the coil at temperature theta degree centigrades. R naught, resistance of the coil at temperature 0 degree centigrades. Alpha, temperature coefficient of resistance. You can't just leave it like that. You have to say for whom, because that depends on the material. So we can say temperature coefficients of resistance of the coil. Alpha, theta, temperature. Theta is temperature. Alright. Next. The figure shows a rough sketch of an incomplete setup that can be used for this experiment. What is there? You have the beaker, the coil is immersed, and from that it goes to item 1, the coil is here. This is what they say 2. Wire gauge 3. What are the items marked as 1, 2 and 3? 1, they say it goes to item 1. So where does this go to? It usually goes to the meter bridge. They very clearly said we are using the Wheatstone bridge. So we can say item 1 is the meter bridge or Wheatstone bridge. Meter bridge. You remember? You will have this is how the meter bridge is going to be. Right. You connect the battery with the switch, and if you want a rheostat also. And then here you have a known resistance. And this is where you are going to connect this R theta. R theta. So these two wires should go to this place. Right. So where does it go to? It goes to the Wheatstone bridge or meter bridge. 2. Beaker. Correct? Beaker with water. Or we can say water bath. Or we can say beaker with water. Or you can say even hot water bath. 3 is Bunsen burner. As per this diagram, those are 1, 2 and 3. What is the main purpose of using wire gauge when heating the liquid? I don't know how many of you have noticed, we keep a tripod. On the tripod we keep a wire mesh or wire gauge, and on top of that only we keep the beaker. So what's the purpose of that wire gauge? This flame is just going to give the heat at one point only. By keeping the wire gauge, you are spreading it. So the heat will be transferred to the beaker evenly everywhere. Otherwise at one place only it will be heated. Right. So sometimes like you have to stir heavily to spread that heat everywhere. Sometimes the beaker even get overheated at one point and can crack. To avoid all that, we keep that wire gauge. So what's the purpose of the wire gauge? To heat the beaker evenly. Next, apart from the Wheatstone bridge arrangement and two other items which are not shown in the above figure are necessary to perform this experiment. What are they? I think like the previous experiment, here also they did not mention the thermometer and the stirrer. That's what they're asking. See, same question. That's the importance of doing past paper. Same. What is it? Thermometer and stirrer. I already explained the purpose of using these two. It has been decided to use coconut oil instead of water as the liquid in this experiment. Give two scientific reasons for this decision. See, coconut oil, its boiling point is high. Water will boil at 100 degrees. So when you use coconut oil, you can even go for temperatures beyond 100 degrees. Point number one. Point number two, compared to water, coconut oil doesn't conduct electricity. So when you have the coil like this, look at this. You have a wooden rod and the coil is like this. This is how the coil is. And if you keep it in the water, from one line to the other line, at least there will be a little bit of current leakage through water. Right? Water can conduct current, whereas coconut oil can prevent it. Right? So those two are the main reasons why coconut oil preferable. One, the electric conductivity of coconut oil is less than that of water. So across the wiring, so like from one ring to another ring, through the liquid, current being conducted can be avoided or can be minimized. Two, water, you cannot go beyond 100 degree. Usually in the normal atmospheric pressure, around 100 degree water starts boiling. Whereas the coconut oil doesn't boil at 100 degree. How do we know this practically? I don't know how many of you have this experience. If you want to fry something, right? You take coconut oil in a container and you heat it up. Let's say you're going to fry let's say some potato or french fries or piece of fish, right? So when you are about to drop that potato into the coconut water which is heated, by mistake, let's say a water drop falls into that. Very often it happens. Sometimes you might have washed your hands and there might be water drops in your hand. When you go above the container, the water drop falls. And have you noticed what happened to the water drop? Immediately it gets boiled. That's why that blasting sound it comes. When the water drop falls into heated oil, immediately small cracks come and the water evaporates. Which means that coconut oil is already above 100 degree. Otherwise, what should happen? If it is not above 100 degree, when you put water should go under the coconut oil now. Because water has more density, so water should comfortably go under the oil and it should stay there. But it doesn't stay there. It immediately blasts and boils. Why? Coconut oil, the temperature is beyond 100 degree at that point. Right. So practically you should have realized this when you go to the kitchen. If you go to kitchen. So let's say coconut oil can be heated beyond 100 degrees centigrade also. This will give readings in a wider range. This will give readings in a wider range. Second one, that's about coconut oil's heat. Other one, the electric conductivity of coconut oil is less than that of water. Therefore, from one ring to another ring of coil, electric leakage through the liquid can be minimized. Clear? It can be minimized. Next. A student argues that when using a Weissenbridge and arrangement, a current has to be set up through the coil and that current may affect the accuracy of the measurements. Would you agree with this argument? Yes or no? Same thing we discussed earlier also. See, the 10-volt battery is connected to this coil. So, because the current flows through the coil can be heated up. Right. So, when you measure the water's temperature, sometimes the coil's temperature, because of the current, can be slightly higher than the water's temperature. Right. So, can it have an impact? Yes. Yes, that's what they ask. Would you agree with this argument? Yes. Explain your answer. Due to the current flow through the coil, the temperature of coil can be higher than that of the liquid. Next. Draw a rough sketch of a graph that shows the expected variation of the resistance of the coil with temperature. X theta versus theta. Label the axis with appropriate symbols identified in A above. Wait, in A, what are the symbols to be used? R theta and theta, not x theta. X theta was in the previous question, yes? R theta. But same graph it is, same graph. R theta equals R naught plus R naught alpha theta. So the graph has to be something like this. Upward sloping graph with a positive gradient, positive intercept. When you say upward sloping, it's positive gradient, and there has to be a positive intercept as well. A graph with positive gradient and positive intercept. Clear? Right. So, that's all in this 2010 paper as well. Did you see how straightforward and how easy these questions are to answer? Ideally, if you have done these past papers also, then it becomes even more easier. Because you saw even within these two papers, half of the questions were repeated. They might have changed the wordings, right? But the same thing they asked this graph. They asked about the current flowing through the coil and that have an impact on the temperature. They asked about the thermometer and the stirrer missing in the diagram. See? So, common stuff are being tested again and again. So, first thing, go through the experiment few times and understand each step, why we are doing like that, how we are doing it. Second step is doing all the past papers and making yourself comfortable to face any question in the exam. Clear? So, that's all in this experiment. Let's move on to the next experiment in the next session.